Hey everybody, welcome back to physics. We discussed the basics of waves. Now we're going to be moving into wave phenomena, which is basically what waves do and how they interact with the universe around us. Today we're going to be discussing one particular wave phenomena, and we're also going to be discussing some tools that we use in order to better understand how waves interact with the universe. But before we get started, I kind of want to show you guys a quick video to give you a little preview of what we're going to be discussing in today's lesson. All right, I want everyone to listen closely. This was recorded with a potato. All right, so you're listening. You hear a siren. There's the fire truck. What happened there? I'm going to play it again. So you probably have experienced this at some point in your lives with an ice cream truck, a siren, anything like that. But listen closely and watch what's happening with the fire truck as it passes by. Okay, here. The pitch changes as the fire truck passes us. Is the fire truck messing with us? Are they changing their siren as they pass us by? This is the first example of one of the wave phenomena we're going to be talking about, which is called the Doppler effect. How the pitch or the frequency of the wave changes as it passes us. It has to do with sound waves, but it also has to do with all kinds of waves. We'll be discussing that in just a second. But first, let's formally define wave phenomena. What wave phenomena are is what waves do and how waves interact with the universe. Just so you guys know, with this word, phenomenon is a singular phenomenon, but phenomena with an A at the end is plural because there's a few different things that waves do inside of our universe. And here are a few of the questions we're going to be answering as we discuss wave phenomena. Talking about that siren, why does the pitch change as it passes by? Some other things we're going to be doing in some later lessons is, why do ocean waves bend and spread as they pass through small openings in the rocks? What happens when waves hit a boundary? And what happens when two waves collide, right? We'll be discussing all of these things, but for today's lesson, we're going to be discussing this first question here. Why do pitches change of waves if we have some motion between the source and or the observer of a wave? Okay, so our goal is to discuss the Doppler effect, why the pitch changes. Just so you guys know, in music, the pitch is the note. Higher pitch is higher notes, and lower pitch is lower notes, right? And that has to do with the frequency of the wave. Before we discuss exactly what's going on with the Doppler effect, I want to discuss some new tools that we're going to be using to discuss waves. All right, so in order to discuss wave phenomena, we need to discuss two new tools that we're going to use in order to analyze how waves interact with our universe. And those two tools that we're going to discuss are wave fronts and wave rays. Just two new lines that help us track these waves as they move through the universe. So the first tool we're going to discuss is what we call a wave front. What a wave front is, it's made up of all points on a wave that are vibrating in phase. So take a look at this complicated diagram here on the left. These blue lines are what we call the wave fronts. As you can see, we have many waves here. All of these waves are given in red, and these waves are vibrating as we move out. Something we discussed in previous lessons, we could talk about the wavelength of these waves, the frequency of these waves, the different points that are in phase. What wave fronts are is they pick points in phase for these waves and they draw a line. And then they find the next point in phase and they draw a line. So these blue lines are what we call the wave fronts. Here they picked all of the crests of the wave, but we could have picked the troughs or just any 2 points in phase. And by drawing these lines, we can track how all of these waves move as they propagate throughout the universe. So in previous lessons, we were looking at singular waves, right? We were seeing how those waves wiggle. But waves don't live on their own. Like imagine you flicked the water in a lake or a pond, you would see ripples of the wave move outward. I could pick any singular wave, but if I want to track how all of those waves are moving outwards from that point, wave fronts are a useful tool for us. The distance between any two wave fronts is always going to be the wavelength of the wave, okay? These are the successive wave fronts. The wave is propagating in this direction. This tool works for sound, works for light, works for water waves, but we can, instead of looking at the individual wave itself, we can look at these fronts in order to see how the wave is moving through the universe. Okay, notice this word here. That's the next tool that we're going to be discussing, is the wave ray. So the wave fronts are these lines as they move, each point in phase of the wave, but the direction that the wave is propagating in, or the direction of motion of the wave, is what we call the ray. So a wave ray is simply an arrow that shows the direction of wave propagation. You might have heard this word ray in math. In math, we define a ray as a line that starts at a particular point, but then goes off to infinity based on this arrowhead. Okay? So we can say that the wave started here or at some point in this direction, and the wave is heading in this direction, and the ray is drawn perpendicular to the wave fronts. Again, the wave fronts are lines of all the waves wiggling in unison. So if you can imagine it, we're kind of looking down on these waves, and the waves are wiggling in this direction here. Just like this, heading that way. Another way we could look at fronts and waves, and fronts and rays, is this diagram here. We have a candle. And we learned in previous lessons that light could be modeled as a wave, an electromagnetic wave. So the light is originating at the flame and heading outwards from the flame. The direction that the light is moving in is given by these rays. The rays start at the source of the light and they head outwards from the light, showing which way the wave is moving in. These circles here are the wave fronts. The wave fronts are drawn at all the points in phase of the wave. So the wave is wiggling this way. So we can say all the crests of the waves are here, radiating outwards from this point. This is going to be really useful for us as we discuss the Doppler effect from the video we just saw, and some other wave phenomena that we're going to be seeing in some future lessons. Okay, so I hope you're feeling okay with fronts and rays. We're going to be using this tool of wave fronts to try to explain why that siren had a high frequency as it was heading towards us, a high pitch, and a lower frequency as it was moving away from us, a lower pitch. Okay, try not to get hypnotized from this slide. Before I discuss what's going on in the diagrams, the definition of the Doppler effect is the apparent change in the frequency, and thus the wavelength, of a wave when the source and the observer are moving relative to one another. Okay, so take a look at this diagram here, ignoring this one. We can imagine that this is a point source of a wave. Here we can focus on sound, but this is true for any type of wave that we'll observe in our universe. Let's say this source is producing some kind of sound, and that sound radiates outwards from this point. We could say that this is a speaker. Now, if I took this speaker and I pushed that speaker, like on a rolly cart or something, and the speaker can start moving off to the left, you'll start seeing why the Doppler effect works the way it does. So here we can see the speaker start to move. What happens as the speaker moves, it's not changing the sound it's producing, but as it moves, these waves start grouping and crowding on top of one another as it moves off to the left. How we interpret sound depends on the frequency of the sound. The higher the frequency, the higher the pitch and the higher the note. So as this moves off to the left and we're listening in over here, we're starting to hear these waves as they're grouping on top of one another. We hear a higher pitch if we're hanging out here off to the left. And if you look off to the right, you'll see that the waves start separating a bit more than they were at first. So if you hear to the left, you hear a higher pitch. and if you're here to the right, you hear a lower pitch. You experience a higher frequency wave over on the left, and you experience a lower frequency wave here off to the right. And this has to do with the relative motion of the source and the observer. In this case, the source is moving, right? And because the source is moving, we hear a different frequency depending on where we are and compared to the motion. Okay. And notice that this is apparent. If we were sitting on this speaker as we moved, we wouldn't notice any change in the frequency of the sound. And I have another video for us to see that in effect. Take a look here. So before I start this video, here's what's happening here. We have a person in a car driving. The passenger, not the driver, has a trumpet. And as the car is driving, the trumpet is going to play a continuous note. And we're going to see the difference of experiencing that note inside of the car as we're moving along with the car, or if we're standing at the roadside. So inside the car, here's what we see in here. Moving along. Pay close attention to the pitch of that note. That's the true frequency produced by the trumpet. It's always making that sound. Here's the same video from somebody on the roadside. Listen close. There's that higher frequency, and there's that lower frequency. And this is very important. Notice in the car, the frequency never changed, but as that trumpet passed the observer, it started off high, and then it went down low. So the Doppler effect also happens, not only when the source is moving, but also when the observer is moving. Take a look at this diagram here. So in the previous example, in the video and the animation I showed you, we had the source moving. But in this case, the source is stationary and the observer is moving. The green is who's listening to the wave. The red is creating the wave. As the green moves in, it starts experiencing those waves at a higher frequency. But then as it moves away from the red, it experiences them at a lower frequency. There you go. So the green would also experience a Doppler effect here, experiencing a higher frequency as it heads in and a lower frequency as it heads away. This describes things like ice cream trucks and sirens as they're moving relative to you. But it also describes like ocean waves, right? If you're in the ocean and you have a source producing a wave, if you move closer to that source, you'll experience those waves at a higher frequency. If you move away from that source, you'll experience those waves at a lower frequency. Both of those experiences are manifestations of the Doppler effect. So this Doppler effect works for all types of waves: sound waves, ocean waves, and even light waves. So if we have a source of creating light, and that light is moving, granted that source of light has been moving very, very quickly. But if it's moving quickly enough, we could measure and observe a change in the frequency of light. Now, what does it mean for the frequency of light to change? Something that we talked about in a previous video is that the frequency of the light corresponds to what type of light we're experiencing. If we're in the visual spectrum, if we have a higher frequency light, we're looking at bluer light, more purple light. And if we're at lower frequency light, we would see redder light, more orange light. Okay, so let's say we have something producing light and it starts moving through our universe. We could say very quickly. If it's moving very fast, if we're on this side looking at this thing, it's going to look bluer than we would expect it to look. Now that seems crazy, but that's something that we have observed out in nature, particularly with astronomical phenomena, things out in space. If that object is moving towards us, it's going to look bluer than we would expect it to look. And if it's moving away from us, it's going to look redder than we expect it to look. And we actually use the Doppler effect to prove that the universe is expanding. The universe itself is stretching, getting bigger and bigger and bigger. When we look out at any distant object out in space, we know what that object should look like because we know the molecular composition of all the stars out in our universe. And as we look out on these stars, all of these stars look redder than we expect them to look. Every single star we look at. So if we're here on Earth and we're looking out at all of these stars and they all look redder than we expect, that means that all of those stars are moving away from us. There's a few ways we could try to explain this. The most likely explanation for what's going on here is that the universe itself is stretching and expanding and getting bigger and bigger. And as the space in the universe gets bigger and bigger, all of the objects within it is going to move away from one another. So here on Earth, looking at all these stars, if they look redder than we expect them to look, this is great evidence that the universe is expanding. So the Doppler effect doesn't only affect waves here on Earth, it affects waves everywhere in our universe. If we see an object looking bluer than we expect, that object is heading towards us, and we could say the light from that object is blue shifted. But if an object is moving away from us, then we could say the object is red shifted, producing a light that's redder than we expect it to look. And that helps us figure out the relative motions of things out in space. Okay. So here's a quick summary of everything we've talked about so far with the Doppler effect. When the source and the observer are approaching one another, whether they're moving together or just the source is moving or just the observer is moving, the observed frequency is higher than the actual frequency of the wave. For sound, this is a higher pitch. For light, this is a bluer light. When the source and the observer are moving away from one another, the observed frequency is lower than the actual frequency of the wave. Keep in mind that if the frequency is higher, the wavelength has to be shorter. And if the frequency is lower, those waves repeat less frequently. That means that the wavelength has to be longer, right? A lower frequency corresponds to a higher wavelength. And something else to keep in mind is this change in frequency is only apparent. This word apparent kind of just means what we observe. The actual frequency of the wave depends only on the source of the wave. So if you're sitting in the fire truck, that siren doesn't ever change pitch. The frequency that you hear riding along in the siren is always the same. But as that siren passes somebody on the roadside, it sounds at a higher pitch, higher frequency as it heads in, and a lower frequency, lower pitch as it passes by. Okay. And something that I mentioned before, when frequency is affected, wavelength is also affected. They're related to one another based on that equation that we saw in a previous video. V is equal to F lambda, right? Speed through the medium doesn't change, or speed through the universe doesn't change. So if we change the frequency, we are also changing the wavelength. As frequency increases, wavelength has to decrease. And when frequency decreases, wavelength has to increase. And when we're talking about light, the Doppler shift is observed as a blue shift, higher apparent frequency if it's heading towards us, or red shift, lower apparent frequency as it's moving away from us. Okay. One last thing I want to do for this video is I want to discuss some examples of the Doppler effect based on this diagram here. Something you will be expected to do is qualitatively describe what's going on with the Doppler effect. Things like, is the apparent frequency increasing, decreasing? What's going on with the wavelength? You won't have to do any calculations here, but you should understand how the Doppler effect works based on any information or diagrams that they give you. So take a look at this diagram off to the right. We have 4 points, A, B, C, and D. And then we have a bunch of wave fronts that are given inside of the diagram. Okay? So based on this diagram, let's see if we can answer these questions. Question number 1. The source of the sound, assuming that this is a sound wave, is moving towards which point? A, B, C, or D? Okay. Well, based on all the animations and the diagrams that we saw, the source of the wave should be coming from here. And notice that the waves are crowded on this side of the diagram, right? And if that's the case, the source of the wave has to be moving in this direction because we have a higher apparent frequency over here. Because the waves are crowded, we have to be moving towards point B. B is the correct answer there. Okay. Now comparing the frequency observed at point D, the frequency observed at point B is higher, lower, or the same. Well, the source and the observer are heading closer and closer to one another. And as you can see, like I said before, those waves are crowded on top of one another. So we have a higher observed frequency over here at B. B is kind of like as the siren heads in, we hear that higher pitch, where D is the lower pitch once it passes by. So point B is higher. It observes a higher pitch than the actual source that's creating that sound. Compared to the wavelength observed at point D, the wavelength observed at point B is what? So here we were looking at the frequency, now we're looking at the wavelength. So take a close look at the wavefronts here. I said earlier on that the distance between the wavefronts tells us the wavelength of the wave. Here we have not much distance between each one of these wavefronts, but closer to B we have more distance. So getting closer to B, the wavelength is lower. And finally, if this source starts moving faster and faster, what's going to be happening to the frequency heard at B? Well, if this moves faster, those waves start crowding on top of one another even more. So if they're crowded more, that means those waves are repeating more frequently, which means the frequency increases. Okay, and that answers those 4 problems. The Doppler effect also explains why we can break the speed. We could break the sound barrier while we have sonic booms. I don't know if you've ever seen videos of like supersonic jets, but as those jets go faster and faster, they eventually break the sound barrier. You hear a big sonic boom, and if you're close by, you can actually feel it. And then the waves, and then the jet could go faster than the speed of sound. What's happening is, as that jet goes faster and faster, it's creating sound from the engines, everything inside the jet. So as it's going faster, those waves start repeating more and more and more frequently. And eventually, remember, the speed that these waves can actually move can only go as fast as the speed of sound. So as the jet approaches the speed of sound, those waves start getting more and more and more crowded until eventually there's like a wall of air, of high pressured air, as the jet and the sound that's going off the jet start moving at close to the same speed. And eventually the jet gets through that wall of air, and that's what creates that sonic boom. So breaking the speed of sound has a lot to do with the Doppler effect. Okay, so that'll do it for this video. I hope everyone's doing well. We're going to be using fronts and rays to discuss some other wave phenomena that we'll observe out in our universe. We'll do that in a future video. Hope everyone's doing well, and I'll see you next time.